Hello. I'd like to give you some advice, suggested approach for approaching applied optimization problems. Applied optimization problems are ones, they're word problems, where you told some story. Oh, you're making a box, and the top of the box takes so much material, and the bottom of the box takes so much material. What's the size of the box that we should make? Oh, you're traveling along these two roads. We have these two modes of travel, and they're of different speeds. What's the optimal route that we should take? What's the minimum distance we can travel? Those kinds of things. So the word problems, I'm not going to do one in this video. That's a subject for another video. I just wanted to give you advice for how to tackle these word problems, where you're supposed to find You're supposed to do optimization, right? You're supposed to find optimal values, minimums and maximums, and you're not given a function, right? You're not given your objective function, where the objective function is the function that we're minimizing or maximizing. You're not given it. You've got to suss it out somehow. You got to come up with the objective function, and that's what makes these for many people challenging. But that's why they're so rewarding, because this is really where the rubber meets the road in terms of derivatives and the work we've been doing in terms of optimization. Because we can solve real world problems using what we teach in Calculus 1. And you may find some of the problems to be pedantic in a way, and that's because we continue to train you, and we expect you to go on and do stuff later in your life. And if nothing else, I want you to take away from this class in terms of optimization, thinking in terms of derivatives, critical points, and decreasing the first derivative test, second derivative test, in terms of finding optimal values in your life, and in phenomena that you encounter out there in the world. So I think there's a general framework for approaching these. Okay. So my general advice is to first, and this is my most important advice, draw a picture, right? Draw a picture of the scenario that you're given. Draw a picture of the box. Draw a picture of the roads. Draw a picture of whatever it happens to be, the fenced-in yard, something like that. Draw a picture. And I think that you should label everything. You should label everything in sight. That means making up things. You have to make up names. You're probably not given names of things. You probably have to let them be yourself, right? So like choose good names, like X is horizontal distances, Y is vertical distances, Z is, like push-outs in terms of depth or the thickness of something. H's are heights, right? V's are speeds, whatever it happens to be. You're going to make up names, and you're just going to label everything. And this is a draft. You're probably not going to make a great one at first. Probably as you go and work out through the problem, you're going to find that, oh, I didn't realize, or I wasn't thinking about that the right way, whatever happens to be. And so be willing to start over. There's no shame in starting over. It's totally fine. You just keep starting over. These two things, a labeled diagram, will lead you to come up with the objective function. Right? We need to know what is f of, h equals. I like calling the objective function omega because it really pops. That symbol just stands out to me, right? And so I like calling my objective function omega because what do I do with omega? I optimize it. So it's easy once I set myself up to kind of do the right thing if I choose symbology. There might be some constraints in this, and so I think that step 4 is identify the interval AB over which we're optimizing. So it might be like all positive numbers. So from 0 to infinity. Or it might be from like 1 to 2, something like that. And then 5, finally, once you've identified the interval, you have your objective function. Now you're ready to optimize. Right? And so that's, we need to like go like f prime equals 0 or omega prime equals 0, right? We're finding the crit points. These are also possibly does not exist. So your crit points were the first derivatives. And then this also includes the classification of those points. So as a final step, in conclusion of the optimization, is to classify. And then the last thing that I think you need to do is you want to conclude, right? We're going to like report back. What did we find, right? Like we're going to make our conclusion nice and pretty. And if this doesn't look nice on the paper, then we're going to write it up nicely. Okay. So that might mean going back and drawing a picture, labeling everything, and doing these things so that it just looks really nicely. I think you're not done with one of these problems until like it looks pretty and is organized. And I think it's really important that you make the effort to put in the organization to make it look nice, because that's like, how do you know when you really have this process down? Is you can just like beautiful one piece of paper, probably. A lot of these problems are going to take like a whole piece of paper. It's going to look pretty. So that's my general advice. We didn't do an applied optimization problem. I'm just suggesting a general framework for how to approach them. And I think you should practice this. So we'll practice this in another video. But until then, thank you for watching and good luck. Bye.